this computer. Well, let's hope it's recording. Yes, I think it's recording. Okay, so we were talking last time about various things such as linear independence and completeness. And let me just remind you about linear independence and linear dependence. A set of vectors is linearly dependent if there are, say, n vectors. They're linearly dependent if you can find n numbers, not all zero, such that this sum vanishes. And a set of vectors then is linearly independent if you can't do that. And what's quite important is that a set of if a set of vectors is linearly, if a set of n, well, first of all, that a set of linearly independent vectors is maximal in the set if the addition of any other vector to the set makes the enlarged set linearly dependent. So if you have a maximal set of linearly independent vectors, then basically you're good to go in this sense, namely that a set of n linearly independent vectors that's maximal in the vector space can represent every vector in the space as a linear combination. So any vector u in the space can be represented in terms of the n of the maximal set of n linearly independent vectors. And the proof of this is quite simple, and I think it's worth going through in class now. Namely, if we enlarge the maximal set by including in any vector u not already in it, then the bigger set will be linearly dependent. So there'll be numbers C0 up to C1, Cn, not all zero, that make the sum vanish. Now, if C0 were zero, then this sum would be zero. And then the V's would be linearly dependent, but we've assumed they're linearly independent. So C0 is not zero, and we can divide by it, and then we can express the arbitrary vector u as a linear combination of the V's. So a maximal set of linearly independent vectors can span any vector in its vector space. And the number of vectors in a maximal set of linearly independent vectors is defined to be the dimension of the vector space. Remember to ask questions and to use chat to ask questions. Okay. So that's the dimension of a vector space. I think we can skip this section. This basically says that if you had two bases of a vector space, then they have to be the there's have to be the same number of vectors in each space. In other words, this definition of the dimension of a vector space as the maximum number of linearly independent vectors in the space makes sense. This is something of a confusing proof, so I'm going to skip it and let you read it at your leisure. If you want, we can bring it up in Wednesday's problem session. Now there's a question here. Let's see, something about, okay, great question. The question is, what's the difference between the identity matrix and the Kronecker delta? And the difference is that the identity matrix is an abstract quantity, and and its representation in any basis is the Kronecker delta of that dimension. So the identity matrix in any given basis is always represented by the Kronecker delta. This is a funny example. This is an example of how of the connection between an abstract linear operator like the identity operator or the identity matrix and its representation as a matrix of numbers. What's funny about this particular example, though, is that the representation of the identity operator is the same in every basis, whereas most operators that are, in other words, abstract linear operators, their representation, as we'll see later today, depends upon the basis that you choose. And if you switch to a different basis, you'll get a different representation for the linear operator. Okay, so let's go now to orthonormal vectors. And the reason why people like orthonormal vectors is that it makes computations a lot simpler. So suppose we have n linearly independent vectors, v1 to vn. We can then, they're linearly independent, we can turn them into a set of vectors that are orthonormal, represented by capital U's, and therefore that will have in our chosen inner product an inner product that's just the Kronecker delta. There are many ways to do this because there are many such sets of orthonormal vectors, and we're going to use the Gram-Schmidt method, but as we'll see in a moment, the Gram-Schmidt method isn't unique either. But so let's first of all say we've arbitrarily chosen to number these n linearly independent vectors in a certain way. And so now we're going to pick the one we numbered 1, and we're going to normalize it. And so our first vector in the orthonormal set U1 is already automatically normalized. So then we define U2, lowercase u2, as V2 plus C12, some constant that we'll determine in a moment, times U1. And we require that C2 be orthogonal to U1. By orthogonal, we mean that this inner product vanishes. And of course, inner products are linear in as you go to the right, they're linear in the right-hand vector and antilinear in the left. So here, U1 inner product U1 is just unity. U1 inner product V2 is just this here. And so for this to vanish, C12 has to be minus U1 V2. And so then we have an expression for the unnormalized vector that's at least orthogonal to U1, and that vector then is V2 minus U1 V2 U1. And to normalize it, we just take the vector, take its inner product with itself, take the square root, and divide by, and use that as in the denominator. And then we get a normalized vector U2. So now we have a set of 2 orthonormal vectors, U1 and U2. The next step basically tells you how the whole thing goes. We then set U3 to be a linear combination of V3, U1, and U2, and we require it to be orthogonal to U1 and to be orthogonal to U2. The orthogonality with U1 gives us that the inner product of U1 with U3, well, let's see, U1 with U1 U1 is normalized. So this just, wow, this just gives us C13. the inner product of U1 with U2, well, they're orthogonal. We've constructed them to be orthogonal. And then what we're left with is just the inner product of U1 with V3. And so this identifies V13 as being minus this. Similarly, we want this new vector U3 to be orthogonal to U2. So we form the inner product. This inner product vanishes. This one is unity. And this one, we don't know yet, but now we see it has to be minus, C23 has to be minus U2, U3. And so now we have constructed a third vector that is now orthogonal to both U1 and U2, and then we normalize it. And as we continue in this way, we then have, let us say, K minus 1 orthonormal vectors UI. We set UK equal to VK plus those. We require it to be orthogonal to all the first K minus 1 capital U's. And that then, we then get the coefficient. Let me make this a little bit bigger, this thing. And so the UK then has to be equal to this, and the normalized vector is that. And so in that way, that's called the Gram-Schmidt process. There are other procedures that also to get to orthonormalize a set of linearly independent vectors. Okay, we've got a question here. When you normalize U3, why is the inner product in the denominator rather than U3 squared? Well, when you normalize, well, let's go back. We know what U2 is, it's this. And so we can, what the norm of U2 is, and we can divide by it. And now this then is automatically an orthonormal, this now automatically is a normalized vector, because if you take the inner product of U2 with itself, you get in the numerator the inner product of U2 with itself, and the denominator you also get the inner product of U2 with itself. So that gives unity. I'm a little bit confused as to the question. Let me repeat the answer. The reason this works is that if you take the inner product of U2 with itself, you'll see that you get unity. And then if you go down here, you take the inner product of capital U3 with itself, you can see you get unity. Somebody is pointing something out here. Well, let's just look at this back here. If you take the inner product of this with itself, you get in the numerator U1, U2 dot U2, or U2 inner product U2. In the denominator, you also get U2 inner product U2. So that's unity. So the way you normalize a vector is you take the vector and divide it by its norm. Its norm is the square root of the inner product of the vector with itself. Okay, well, it's good to ask questions. Remember C.N. Yang, the Nobel laureate, who not only was key to inventing, was one of the discoverers of the breakdown of parity conservation and the weak interactions. He also, together with Mills, invented Yang-Mills theory, which is absolutely critical to all of modern theoretical particle physics and quantum field theory. And in fact, You can even think of general relativity as being, in a certain sense, it's certainly in the spirit of Yang-Mills, but it's not quite the same thing. Anyway, let's go on to let me just mention something. If you suppose we originally had n vectors that were linearly independent, we numbered them arbitrarily 1 through n. If we chose a different order, if we called this one U2 and this one, I'm sorry, if we called this one V2 and we called this one V9 and renumbered the others, so we had a consistent set of numbers, then we went through the Gram-Schmidt process, we'd get a different set of orthonormal vectors. They'd still be orthonormal, but they'd be a different set. So there are many different bases, every vector space has infinitely many sets of orthonormal basis vectors. In any vector space, in other words, you have infinitely many sets of orthonormal vectors. In fact, infinitely many maximal sets of orthonormal vectors. Okay, let's get now to outer products, which we talked about on Wednesday, and I think also on Tuesday. And here's the abstract description of it. And the way it had to be discussed before Dirac, well, I don't even know if it was discussed this way, probably was. Anyway, for any two vectors f and g, we make an outer product operator A that maps every vector h into a particular vector f multiplied by this scalar. So A on h is the vector f times this number, or this number times the vector f. Now, how do I get that to be big enough? I don't understand how this works. Let's try that. Okay, so let's verify that this operator A, defined in this way, is linear. Well, it's linear because A on this is the vector f. Remember, A on any vector is the vector f times some number, and the number in this case is g times the number z times the vector h plus the number w times the vector e. And then because inner products are linear, we get linear on the right element, we get this expression here, and that we can rewrite as ZAH plus WAE. And that, of course, is the definition of a linear operator. A linear operator is an operator such that on the sum of two vectors gives you the number times its action on one vector plus the second number times the action on the second vector. So that's what we mean by a linear operator. The reason, there was a question here, why is an orthonormal basis preferred? Well, it's just that when you compute with these vectors, how shall I say? All right, let me just give an example of why it's easier. It simplifies computation. And one reason is that if you, as we'll see in a few minutes, the identity operator is a sum of outer products of orthonormal vectors. If they weren't orthonormal, we'd have to multiply each outer product or divide each outer product by the squared norm of the orthonormal vector. So it would be a more complicated sum. Another reason is that in quantum mechanics, the probability of a state being of a state having a given property is the inner product of the two vectors that represent that, and then the absolute value squared of that. But if the states are orthonormal, if the states are normalized, I should say, and so if not, you have to take that quantum mechanics formula and divide by the norm, the product of the norms of the two states. In fact, the product of the squares of the norms of the two states. So just everything, life is easier with orthonormal vectors. That doesn't mean you have to do it. Often we don't, often we leave the normalization aside, but it's just, in most cases, it's vastly more convenient. All right, so we now know that this is, okay, hold on, we've got another question here. It's great that we've got these questions. So in 1.29, can Z and H and then W and E be interchanged? Oh, yes, they can be interchanged. A number times a vector is the same thing as the vector times the number. It's just conventional to write the number in front of the vector if it's a column vector. If it's a row vector, sometimes you write the number to the right or to the left of the row vector. It's just a convention, but you're absolutely right that we could have written this as A on HZ plus EW, and it would have come out to be the same thing. And we could have taken this Z and put it over here, and we could have taken the W and put it over there. But it's this makes things easier to read because the action of the number, the action of the linear operator on a number is trivial. And so we just pull it out to the front, and as usual, we put in second place the quantity that's more complicated that we can think about. Anyway, it's great that we're getting questions. This may mean that online instruction is better than in-person instruction. Anyhow, let's go on from there. We have, let us say, F, G, and H are vectors with these components in some basis. Then the linear transformation A on H is Aij, Hj, and just translating this down here into component form, it's Fi, and then the inner product of G with H, which is G sub J star times Hj. And we're doing the star because in general, you know, in quantum mechanics, we deal with complex numbers, and consequently, we always put a complex conjugation there. Anyway, in that basis, A is a matrix with entries. You see A fits right here. This is A, or I'm sorry, this is A. And so what is Aij? Well, Aij is Fijj star. So comparing these two, we see that Aij is that. And that, in fact, though, is the outer product of the vector F and the column vector F and the row vector G star. Okay. And we did some of these things Tuesday and Wednesday, so I think we can skip this example. You can read it on your own. It's in the book, of course. This is the book, although as I update the book, I update what you see in class. Dirac's notation for outer products is neat. Column vectors look like this. So the column vector ABC is represented as an abstract vector F, and ZW as a vector G. And the complex conjugate there of the two, oh, there's a mistake. Wow. So one, this should be Z star W star. F, though, is right. And multiplying F times G, this is right, and this is right. And then F with F, the outer product is simply this, and the outer product of G with G is this. So you should play with these things and maybe do examples of your own, because my memory is that undergraduates don't get taught in math classes about outer products very much. I could be wrong. Maybe the mathematicians have improved. Dirac notation. So outer products occur all the time in quantum mechanics. And Dirac invented a notation for linear algebra that makes them easy to use. And his notation for a vector is, he called it a ket. And the new thing that he invented was the bra, G. And the reason he chose these names is that if you then can consider the inner product of two vectors, you get the inner product of G with F, you get a bra with a ket. So it's the bra times the ket, like that. But even better, if you have an operator that you call, or a matrix that you call C, then the inner product of the vector G with the linear operator C, or the image of the linear operator C on the vector F, that inner product is GCF, which in his term would be called bra C ket F. So he called it a bracket, bra C for the operator ket. So that was devilishly clever of the man. Well, he was a remarkable man. By the way, his father was a French teacher, possibly a teacher of more languages than French. And he insisted that even though their native language was English, he insisted that they speak French at dinner. And he would punish the children if any of them made a mistake in French at dinner. And so I don't know what one should draw from that, but one thing that I have read is that children exposed to more than one language become smarter than children exposed to only one language. So let's see, there's a question up here. What's the physical significance of outer products? Yes, outer products are operators. They're not necessarily observables unless they're Hermitian. Any similarities between outer product and the cross product? Gee, I would not get, I mean, there might be some relation between the outer product and the cross product. I can't think of what it might be. So I will pass on that. Let's go on with the lecture here, and I'll make the type bigger so that it's easier to read. In Dirac notation, an outer product like 1.28. So let me, why is this giving me a worry wheel? Well, anyway, it presumably would. Okay, I'm getting a worry wheel here. All right, the worry wheel has gone away. On the other hand, so has. All right, let's try to get where we were. We were back before that. Dirac notation, right. Okay, sorry for this. In Dirac notation, an outer product, presumably like this one, AH equals GH, the inner product of G with H times F, like this. In Dirac notation, it reads this way. So you write the outer product, FG, and then let it hit the vector H, and then this is automatically the scalar. And the outer product of A itself is, or A itself represented as an outer product is just FG. So you see that if you identify the operator A with FG, then A on H is FGH, and this is automatically the inner product. So it's really a cool notation. The broad G is the adjoint or Hermitian adjoint of the ket G, and the ket F is the Hermitian adjoint of the bra F. So we can write these relations, and Hermitian adjoint, that process takes you right back to G, and same thing with F. And the adjoint of an outer product is, well, the G becomes the bra G becomes a ket G, the ket F becomes a bra F, and Z becomes Z star. So what you want to notice here is that the number has to receive an explicit complex conjugation when you take the adjoint of an operator, but the kets and bras automatically include the complex conjugation. So let's look in Dirac's notation what the most general linear operator is. Well, it's an arbitrary combination of outer products. So that may be the answer to one of the earlier questions, which I've actually kind of forgotten. If you take the adjoint of that, well, you complex conjugate the number, and you turn the bra into a ket and the ket into a bra, and it turns into that. So these are equations that you want to understand, and you can illustrate them as matrices and play with them yourselves. These equations are used all the time in quantum mechanics. The adjoint of a ket H is, well, the adjoint of this, and writing A as the most general possible linear operator, we see that we just get this thing turns into, this LF turns into FL, the ket K becomes the bra K, and it just becomes this. And then comparing this with that, we see this is FA adjoint. So the adjoint of AF is FA adjoint, or the adjoint of A times the ket F is the bra F times A adjoint. Before Dirac, this was much harder. If the kets, now we're coming up against something quite important now, I think. Actually, all this stuff is important, but anyway, if the kets form an orthonormal basis in an n-dimensional vector space, then we can expand an arbitrary ket in that space in this way. We saw that earlier. Since the basis vectors are orthonormal, we can identify these coefficients by just taking the inner product of the ket F with the bra L. And bingo, we see that's nothing more than C sub L. So the original expression then is F is some CK K, and that's bra K, ket F, ket K. And now if we do what one of the students asked to do earlier, namely we move this number to the, we move this number to the other side, we then have, and then we can factor out the ket F, and what we have is a sum of outer products of K's. Now let's look at this equation. Arbitrary vector F, arbitrary ket F equals arbitrary ket F times this. So this thing must be the identity operator. What sits between these parentheses must be the identity operator. Since it must hold for every vector F in the vector space, it follows that this is the identity operator for that space. So this is really important. And in quantum mechanics, knowing this can make things clearer, because you can often, if you have some complicated expression with operators and bras and kets and all that, you can at any particular time stick the identity operator anywhere in the expression without changing anything, and then you can write that identity operator as a sum of outer products of any complete orthonormal set of kets. And that sometimes makes things clearer. Now, we we didn't know anything about these Ks except that they formed a complete orthonormal set. Complete simply means that they can, that every vector in the space can be represented in terms of them. And so you know what basically you need is you need n linearly independent vectors. You can then make them orthonormal and they form an orthonormal basis, and they can, and just as you can expand any vector in the space in terms of a maximal set of linearly independent vectors, so it's also true that you can express any vector in the space as a linear combination of orthonormal vectors, a maximal set, n being the dimension of the space. So the point now is that every set of kets forms that forms an orthonormal basis gives an equivalent representation, because up here, instead of Ks, we could have used alpha j and summed over j. And so what we learn then is that the same identity operator can be represented in infinitely many ways by choosing the infinitely many sets of orthonormal vectors that form the bases of the various bases of the vector space. And that means that you can expand any vector f both by multiplying the vector f by the identity operator expressed in terms of the alphas or in terms of the k's. And so you get two different expressions there. And this is probably worth plodding through. Namely, let's just sort of look at it here. A on a vector, an orthonormal basis, say bi, what is it? Well, it is, we can multiply from the left by the identity operator, and then we get this expression. We can then identify this number with a sub ki. We can just call that a sub ki. So we now have that any linear operator on any basis vector, orthonormal basis vector, is a sum over the orthonormal basis vectors multiplied by coefficients, and the coefficients like this are like that. So the matrix that represents the linear operator A in this particular basis is this bracket, namely bra bk, operator A, and ket bi. And if a unitary operator maps these basis vectors into another basis, then in this new basis, the matrix that represents A is, well, just as we just take the inner product of A, or the matrix elements of A in the new basis, and we can write the new basis vectors as U times the old ones. And if we take the adjoint there, then we get this expression where we're summing over K and J up to N. And this is a number, this is a number, this is a number, and this is matrix multiplication. And you can see this is the unitary matrix. Well, I haven't explained why it's unitary, but it is. Anyway, it's a matrix U, the UKI matrix element, the JK matrix element of the matrix A, and the LJ matrix element of the matrix U dagger. And in matrix notation, it's so much simpler. It's that A prime is U dagger AU. Okay, there was a question here. Okay, well, actually there were several questions. One was, what does it mean to say it's a sum of outer products? Well, I don't know quite what it is, but the identity operator certainly is a sum of outer products. And as I said earlier, every operator in the linear vector space can be represented as a sum of outer products multiplied by complex numbers. Now, there was a question about 1.49 holds only when K equals L. What is K equals L? I don't see K equals, I don't see L. you're summing over K. We're summing over these outer products BK. So in other words, what we're using is the identity operator is a sum of ket BK times bra BK. And we use that expression for the identity operator, multiplied on the left, and we got this. And K, so the indexes are K and I. All right, so I may be missing something. This does happen. All right. All right, let's just focus for a moment on this. This is the equation that you really want. This is the bottom line in a sense. If you have an orthonormal basis, whether it's the basis alpha or the basis K, you can take the outer product of your orthonormal basis vectors, sum over them. That gives you the identity operator. You can choose any basis you want. You get the same identity operator. And this gets back to a question that was asked earlier about the Kronecker delta and the identity operator. And the funny thing was that the identity operator is represented by the Kronecker delta no matter which basis you have. And so too here, you see, if this were an arbitrary operator, we would have alpha j something jk, and then it would be alpha k that would be summing over, or alpha L or something. We'd have a double sum. And here, if this were an arbitrary operator, there would be a sum over a sum over K and a sum over L, and then something in between depending on K and L. But because the identity operator, this is just effectively the Kronecker delta. And A sub Ki means the kth row and the kth row and the ith column of the matrix A is this number, BKA BI. Okay, let me recall for you the inner product rules in Dirac's notation. So if we have a nice positive definite inner product, like most of the ones, like the ones we use in quantum mechanics and in ordinary geometry, in fact, almost all inner products that we use in physics are positive definite inner products. Then the inner product of a bra F with a ket G is the complex conjugate of the inner product of the bra G with the ket F. The inner product of F with a number times a vector plus a number times a vector is linear in this expression. So you get Z1 inner product of F with G1, Z2 inner product of F with G2, but it's antilinear on the left-hand side. And so Z1 comes out as a Z1 star, Z2 comes out as Z2 star, and then we have F1G, F2G. And then the positivity of the inner product is this, and because it's a positive definite inner product, if the inner product of a vector with itself is 0, then the vector has to be 0. States in Dirac's notation are often written by psi or by their quantum numbers, and one rarely sees plus signs or complex numbers or operators inside bras or kets, but one should. So this is perfectly legitimate Dirac notation, and people ought to use that notation. They do occasionally, but not very commonly. Dirac notation, as I said, is really cool. in it, you can take, you can write the formula for the kth orthogonal linear combination of the vectors VL. It's just VK minus the sum I equals 1 to K minus 1 of the outer product of the orthonormal vectors with the vector K. And so it's just this very nice expression. You then normalize it. So it's really quite, it's just so nice, Dirac's notation. And one thing to keep in mind that mathematicians love to emphasize, and it's that the numbers we compute with are inner products like this and like that. These are numbers, these are complex numbers. And in terms of n orthonormal basis vectors, they are, the things we compute with are the components of the ket F and the basis vector J, like that, and the components, the inner product of the bra G with the basis vector J, we call that GJ star, and we can then use the identity operator formula that I said was so important to derive these things. Now we've got a question over here. Kindly repeat the GS theorem. I don't know what the GS theorem means. What is GS? So maybe someone will tell me what. Oh, Gram-Schmidt. Well, Gram-Schmidt isn't so much a theorem as it's a procedure. It's a way of taking a set of linearly independent vectors and turning them into a set of orthonormal linearly independent vectors. And in Dirac notation, that is a very simple expression. You take the outer product, the very first one would be the very first unnormalized orthogonal vector would be just the very first vector in your set. The second one is this thing acting on the second vector in your set, and this is the identity operator minus simply the U1, which is the normalized version of the first orthogonal vector. And so you just repeat this over and over again and you generate the set. As I said, it's just a procedure. It's not the only procedure. Anyway, the numbers we compute with, as I said, are inner products like that. And in particular, we can, if we insert identity operators, there's no change. GF is G identity operator F. For the identity operator, we can pick any orthonormal basis we want, and that then gives us the a sum over of products of the ket F, the components of the ket F with the complex conjugate of the components of the ket G, or equivalently the components of the bra G. And inserting the identity operator twice, we get this, and we could have used two different bases. This could be the J basis, could be some alpha basis, whatever. Alpha I'm just using as a different label, different name. And using these translations, this just becomes G star A F. And this is ordinary matrix multiplication. So this is column vector F, matrix A. Whoops, what? I don't know what, my mouse is so sensitive, I just touch it the wrong way and the damned screen becomes too small. And somebody may be able to tell me what I'm doing wrong with my mouse. Okay, so in any event, we then get these nice expressions, and we can, what we normally do is we gather these into, we write these as column, we write kets as, we write vectors as column vectors, and and as row vectors, and then the inner product GAF is the complex conjugate of the row vector G, the matrix A, and the column vector F. So basically, one needs one can represent an identity operator many different ways, and the coefficients, the vectors that we get will vary with our choice of basis, but the things that we consider physical and use to compute amplitudes in quantum mechanics are numbers, and these numbers aren't dependent upon your choice of basis. So for example, we can use this basis to compute this inner product, or we can use the alpha basis to complete the inner product. We get the same thing. You see, they're equal. Or we can, and down here to compute this bracket, we can do, we can use the K basis here, the L basis there, or we can use the alpha basis here, the alpha basis there, or we could have used the K basis here and the alpha basis there. And so that's how nice Dirac's notation is. And as I say, we're all far better off because of his contributions to physics. His outer products also show how to change from one basis to another. And for example, the sum of outer products maps the kets of one basis into the kets, the alpha kets of the other. So for example, take this U in this form and act on it with a ket L of one basis. This is orthonormal. This gives us delta KL. This gives us alpha L. So U on L gives us alpha L. So that just changes us from one basis to another. Feel free to read about that as you like it. But this gets back to something that will, to a question that was asked before, namely about unitary operators. And what you see here is that if you have two bases and you just take the sum over the outer product of the orthonormal basis vectors of the two bases, you get a unitary operator. And in fact, it's more general as well. The converse is true. Namely, every unitary operator on this vector space can be written as the outer product of the sum of the kets of one basis with the bras of another basis. Okay, now we've got, so that answers an earlier question, and we'll get to the proof of that later, I hope. So here in 160, why does the inner product of the bra, oh wow, you're right here. Why is this equal to that? Well, because these things are orthonormal. So this, we've made, what we're talking about is an orthonormal basis, and the inner product of the vectors with themselves in an orthonormal basis is the Kronecker delta. All right, I hope that's clear. Adjoints of operators. By the way, the term, we use the term adjoint in physics so often that we just call it adjoint. Mathematicians, as we learned yesterday when fiddling with MATLAB, mathematicians use a more complicated expression. I think Hermitian adjoint is one, and they may have a They also call it the complex conjugate transpose. Anyway, the most general operator on an n-dimensional vector space is sum of outer products, z times k times l, z a complex number. The kets are members of two of the n orthonormal kets that make up a basis for the space. The adjoint of that we've seen is of this form. So if we set z equal to KAL, then I don't know why I said z equal to KAL, but anyway, let's take an arbitrary linear operator, multiply it by the identity operator on both sides. We get this expression. Its adjoint is the identity operator A adjoint I, and so we get these two expressions. We learned earlier that L A dagger K is KAL complex conjugate. Or let me see, maybe I've gone through this. Right, okay, so if we simply, in other words, one way to get this expression is just multiply by the identity operator twice. To get this expression, what we do is we say, well, we're going to take this and we're going to take the adjoint of this thing. Well, we know that the L goes here, the K goes there, and what happens to this? This is a number, so it has to become the complex conjugate of that number. And then this tells us that this expression, inner product of bra L, adjoint of operator A, ket K, is bra K, linear operator A, ket L, and the complex conjugate of the resulting number. And so the matrix A dagger sub KL that represents A dagger in this basis is, well, it's by definition that, and we've just seen that this is that, and so we get it equal to this, and that by just, that's what we call A star KL, or A transpose complex conjugate LK. And that's our definition that agrees with our earlier definition of the adjoint of a matrix as the transpose of its complex conjugate. And by the way, if any of you guys are latex aces and can figure out a really good way of writing transpose, let me know, because this T is a little too big and bold. Anyway, we also can write it this way. G A dagger F is the same as what we mean by G A dagger on ket F. We know this is that. And then A on G is just AG, and then complex conjugation throws it over like this. So these are all equivalent forms, and you should think about that equation enough to become familiar with it. And because as I said, in quantum mechanics, one uses it all the time. And the adjoint of an adjoint is, by some prior equation here that we already learned, well, you just, first the adjoint of that is Z star LK, and then adjointing it again, we get back to ZKL. So adjoint is the same thing. If you take A adjoint, adjoint, you get A back. And we can see that in terms of matrices, because double transposition has no effect, double complex conjugation has no effect. Before Dirac, things were very sad. Self-adjoint or Hermitian linear operators. All right, this is important because it's so important in quantum mechanics. Namely, an operator A that is equal to its adjoint is said to be self-adjoint or Hermitian. These are named after Charles Hermite, who was a French medical physicist. I think he taught at École Polytechnique in Paris, but I'm not sure. Anyway, in the elements of a self-adjoint linear operator satisfy this equation. So we know that K A adjoint L has to be L A K complex conjugate. But if A adjoint is A, then that's K A L. And so that means that the transpose of the complex conjugate of the matrix is the matrix itself. And so that's just these statements. AKL, which is KAL, is K A dagger L because it's Hermitian. And then this thing in general has to be that. And then that is just this. So one also can say that this is, and we saw these things before, that if A is Hermitian, then we can flip this over to this side. That's always this, and that is the same as that. Okay. Now, a few more things are that a matrix that is real and symmetric, or imaginary and anti-symmetric, is Hermitian. So most of the Hermitian matrices that you'll see in textbook examples are real and symmetric, or they're imaginary and anti-symmetric. But that doesn't mean that every Hermitian matrix is either real and symmetric or imaginary and anti-symmetric. And in fact, if you go to if you start with a real symmetric matrix and that's Hermitian, therefore, and you change to another basis, the matrix that you get will still be Hermitian, but it will not in general be real and symmetric. And similarly, if you start with a matrix that's imaginary and anti-symmetric, it'll be Hermitian. If you change to a different basis, it'll stay Hermitian, but it won't in general be imaginary and anti-symmetric. Okay, now suppose we have a ket that's an eigenvector of a linear operator A with eigenvalue A prime. So by that we mean the linear operator takes the eigenvector A prime and leaves it where it is and just multiplies it by the eigenvalue A prime. And we'll see later that Hermitian matrices have real eigenvalues and complete sets of orthonormal eigenvectors. And as you may know, Hermitian operators and matrices are used to represent physical variables in quantum mechanics. This Fiat's example, I think one can skip. If you're somebody who wants to do theoretical physics, you might want to read this on your own or bring it up on Wednesday and we can discuss it in class. Let's now look at real symmetric operators for a moment. In quantum mechanics, we consider complex vector spaces. Well, you can consider real ones also. So this is a vector that's real. These are real numbers. And well, here they're real numbers. There they were complex. And we mean here that K star is K and X star is X. And a real linear operator does that. And it's represented by a real matrix. And if it's self-adjoint, we have these relations. All right, so I think we can skip that. Unitary operators, as you know, unitary operator is one whose adjoint is its inverse. And as I mentioned before, but maybe didn't prove, any operator that changes from one orthonormal basis to another is automatically unitary. So these two bases are orthonormal. So let's form U dagger. Well, U is this, U dagger is L alpha L. And these guys are orthonormals, so this is this, that's the Kronecker delta, and we just get that. And that's a representation of the identity operator. If we go the other way, we have U adjoint U, and that's L alpha L, alpha K K. These guys are orthonormal. We just get and so are these, I'm sorry, these guys are orthonormal, so we have a sum over K, which is again the identity operator. So a unitary operator that an operator that changes one orthonormal basis into another is automatically unitary, and moreover, a unitary operator maps every orthonormal basis into another orthonormal basis. And just to see that, suppose alpha k is the image of an orthonormal basis k, or basis vector k, under the operator u that's unitary, then the outer product of these guys looks like this. This sum is the identity operator, and we've said that u is unitary, so we get that the image of a unitary, the image of one orthonormal basis under any unitary operator is another orthonormal basis. And if we multiply this ket by that bra, and again, we're doing something that one of the students asked, whether we could do things backwards or forwards and so forth. Then what we get is this. We can write alpha as u times that, and then we see this is the identity operator, and so that's u. So we immediately see that this is a unitary operator. In other words, you take this sum of two orthonormal, outer product of two orthonormal bases, and write this one as u on k, you then see that this thing is unitary. Right, orthonormal is orthogonal and normalized. So one of the students asked the question, another student answered. So yes, an orthonormal basis is a set of vectors is orthonormal if the inner product of the vectors with themselves is either 0 or 1. So they're orthogonal and normalized. So every unitary operator maps every orthonormal basis into another orthonormal basis, or into an orthonormal basis. The identity operator is also unitary, so a unitary operator, the unitary operator that's the identity operator maps a basis into itself. Now, one that's really important, and we've got a few minutes left, so I can try to stress this, and it's that inner products do not change under unitary transformations. And that's one reason why they are of use in quantum mechanics. So the inner product of G with F is G. If we stick in the identity operator in the form U dagger U, where U is any unitary operator, and then we use the tricks we've learned, we see that that's UG, UF. And so and now these UG and UF, this will be some other basis. So this would be, this would be a different basis, but the same, effectively the same vector. And what I should have done here was gone to a bracket case, and maybe I did that in the past. Let's just see. I'm just, well, all right, here. You see, if you change the basis, as we've seen here, you change the basis, you still get the same number, the same inner product. And to go from one basis to another, well, this is a unitary transformation. In fact, the transformation in question is this one. And so to go, say, from there to there, what you do is you stick in a UU adjoint there, and you stick in UU adjoint, or U adjoint U, or UU adjoint there, and U adjoint there, and that turns this thing into that thing. So that's what we like about unitary transformations, namely that they, that the things we care about, namely inner products are invariant under unitary transformations. Now, unitary matrices have unimodular determinants. That is to say, the determinant of any unitary matrix is unity. And the reason for that is that determinants are invariant under the transposition of the matrix, and the determinant of a product of two matrices is the product of their two determinants. So one is the determinant of the identity operator, which is just a product of ones. That's the determinant of u dagger. That's the determinant of u times the determinant of u dagger. But this is the complex conjugate of the determinant of u transpose. There's no change when you take the transpose of a matrix. And so this is determinant of u times the complex conjugate of the determinant of u. So that means that the determinant of a unitary matrix is a phase factor. It's e to the I theta for some real theta. And of course, a unitary matrix that is real is orthogonal. And so we have this expression here. We talked yesterday a little bit about Hilbert spaces, and namely that a Hilbert space was basically a complete vector space that had a positive definite inner product and was complete with that inner product. And we'll get to that definition later in, I guess on Tuesday, we'll go over it again. We've been mainly here talking about linear operators that act on finite dimensional vector spaces, but in real quantum mechanics, we talk in terms of three-dimensional space, three-dimensional momentum space, and so forth. And we also talk about a vector space of functions of position and time, these wave functions, and we normalize them by requiring them to be square integrable over three-dimensional space. But these are spaces of obviously infinite dimension. If we only have one space dimension, it still is an infinite dimensional space. We typically have state x prime represents a particle position x prime. X on x prime, x is a Hermitian operator, x on x prime is x prime. These are orthonormal. These are orthonormal in a funny sense because they're zero if x is not equal to x prime, but the inner product of x with x prime is a delta function. In fact, once again, it's Dirac's delta function. It's amazing how many things Dirac has contributed to physics. Now, the delta function is not actually a function, it's a functional. And what that means is that the Dirac's delta function, delta of x minus x prime, is a functional in the sense that it takes any function f and maps it into a number, and the number is the value of the function at the point x prime. So this is sort of a fine point, but you see how what Dirac did when he invented this thing which people call the Dirac delta function is in inventing it, he was basically inventing a whole new field of mathematics called functionals. and there were lots of complaints by people who didn't like that, hadn't heard of functionals and so forth. But anyway, another basis for the same Hilbert space is the states of well-defined momentum. The Hermitian operator P on the state P prime is P prime P. And these guys are also orthonormal in Dirac's sense that P prime is delta of P minus P prime. All right, we're just about at the end. We have less than a minute left. I think instead of going further, I should maybe stop and to ask, is there a remaining question? Also, let me thank you all for asking so many questions. I think everybody is helped by these questions, and you should always send them in anonymously. Now, you want to know about the homework. I'll try to get to that. As I said, I've had some computer crises in the last few days. One is that Comcast turned off internet in my neighborhood for about 3 or 4 hours a couple of nights ago. And then I bought a new iMac, and I was transferring data from my MacBook Pro to my iMac, and I was told by Apple that would take a couple of hours. Well, I started it last night and it hadn't happened this afternoon. And so I had to get help from Apple for that. So I couldn't. Anyway, I'll get to the homework and update the class website soon, and we'll take it from there. You can also send me questions by email, but of course the advantage of doing it through the chat function is that everybody sees the question. At least I hope everybody can see the question, and therefore the answer clarifies the question that probably was puzzling several other students. Now, each time a person asks a question, it's normally true that 3 or 4 or 5 or 10 or 20 other students have the same question. And so it's really good to use the chat function. All right, well, have a nice weekend. Try not to catch anything. This COVID-19, the more I hear about it, the worse it seems to be. It affects let's see, I was reading something somebody sent. Let me just say that this COVID-19 is much worse than I thought. Not only is it very contagious, but it tends to, unlike an ordinary flu that just screws up your nose and maybe gives you a fever and chest and maybe muscle pains, this one apparently in some people attacks every organ of the body, or at least a large number of organs, major organs like the heart, the lungs, and so forth. And so you really want to wear masks and basically stay away from other people because we naturally, if we behave naturally with other people, we come close and we shake hands and so forth, and we get infected. So try not to do that. All right, there was a question here. Somebody had an MS degree from a math department. You can, yes, you can drop the course and sit in the course, but I would, I don't think that my course usually, I don't think this course of mine should overwhelm people. So, I mean, if you've covered the material in the math, when studying mathematics, then yeah, I guess if you have other courses that are really hard because your preparation was mathematics, then yes, you could drop this course and but still sit in it. Sit in on it. There will, however, be a lot of physics in this course, so I'd urge you not to drop it. But you know, if you sit in the course, it's another matter. Anyway, do whatever you and your academic advisor think is best. Okay, well, I'll end the recording and so forth, and wish you all a good weekend, and also hope that you all stay safe, because this is a terrible disease. And by the way, one thing that really annoys me is that if you read a history book, the amount of time or pages or words devoted to the pandemic of 1918, 1919 is minuscule compared to that devoted to World War I or World War II. But more Americans died in the pandemic than in both wars combined. And the damned historians, they don't understand medicine or biology or mathematics or economics, and they skip it all, and they just focus on dates and political figures, which is really stupid. In fact, that's why our government has failed so badly. It's part of the reason that governments have failed to take the pandemic seriously. I hope we all take it seriously. So have a nice weekend. Bye.